where we can initialize that debug arena and have it actually work, right? So what we'll do is we'll say debug render group equals allocate render group. We'll throw it some memory from the transient arena, and then we can go from there. So handmade render group, it needs an asset system too, I guess. So we probably want to do it like this, where we know that we'll actually have some assets. We don't really know what the push buffer size should be. We're kind of just making stuff up. And we'll go ahead and say that this doesn't render in the background because, well, it's not gonna render in the background. So anyway, if we actually get that, now our debug render group should actually do something. Of course, the interesting thing about the debug render group, right, is it's not actually going to do anything until we actually call render group to output, right? And so if we want to, at the end of this, after we do our overlay cycle counter stuff, we can come in here and do render to group to output with our debug render group. So we can even do something like this where we say, you know, if there is one, we would like that to happen. The output target should still be valid, oddly enough. I don't actually know. Draw buffer. And presumably, we can just slap our stuff right on top of the game surface, right? By just saying, hey, render on top of the thing that was already there. Presumably. Now we have a problem, which is that when we do render group to output, you will notice that when we call that, we don't actually have excuse me. And I guess we could even do it tiled if we wanted to, right? We could do this threaded. I'm not sure which one we want to do, but either one would work, right? I don't know where is the render queue? I guess it's the high priority queue. So there we go. So yeah, we can do this tiled if we want to, and all that. But basically, what's going to happen at the end of this, this finish render group thing that we call, which does that sort of the end generation bit. What's interesting about this is the render group itself would need to get recreated at this point. And to some degree, we don't actually want that to happen, right? We would rather have it so that we can have a render group that we can kind of reuse, I feel like. And so what I'd kind of rather do is have like, you know, something like begin render pass or something, or begin render, you know, and end render. Something like this, where when you call begin render, that's when it actually does a generation ID, you know, something like this. And then, you know, maybe it asserts even, oops, assets, that's good. Maybe it asserts that it's not doing that, so it doesn't assert. This equals 0. And then when you end render, it asserts it's not equal to 0. And we could make it so that the asset system doesn't generally return 0. I don't know. Probably can't always do that, so we won't actually say that that's true. But we can certainly assert this one, right? So anyway, so if we do a begin render, end render, then that will all work nicely. And the only thing that we would have to do to make this reset itself, because remember, if you take a look at this, the only thing that actually tracks where we are in the render group is just the push buffer size, right? So if we wanted to, we could just reset the push buffer size to 0, and now we've cleared the render group and can just use it again, right? So we could just do an end render here on the debug render group, and everything is magical and fine, right? And as long as we do a corresponding begin render before we start, everything, again, just peachy. You know, it's kind of like, it's peachy. And so we would have to do that, again, immediately after initializing the transient arena. So that's, you know, we'd want to start the rendering, like so. But off you go. And we could also make a Boolean here even for debugging, which, you know, I mean, we could do something like this, inside render, like that, and say, you know, assert group inside render, and inside render. So we could just do something like this, right? Where we say Okay. Assert that you're not inside a render, and then now you are, right? And similarly here, assert that you are inside a render, and now you aren't. Something like that. You know what I'm saying? And furthermore, the other thing we could do is anytime anyone tried to push to something, right? So, you know, if we took a look in here at like push render elements, we could just make sure that anyone who ever tries to do this, we just assert that we're inside, so that no one can do it outside of one of these passes. And, you know, just giving myself a little security buffer, right? Just trying to give myself a little bit of a safety net in case I make a mistake somewhere. Okay. Same would be true for all of this stuff, right? Just making sure we always have, you know, a render group that's been properly set up. So, okay. So suppose we do that, right? Then when we do begin and end render for the render group, we could just keep rendering to it and reusing it over and over again, which is kind of nice. And that's all good, right? So let's see. Inside render here, off the wrong pointer. There we go. Same with this guy. And so now, for these dudes, right? When we do our allocate render group, we now need to do a begin render on the render group, right? Like so. And now this turns into an end render on the render group. Yeah, finish render group, same thing. This is going to be an end render. And then up where we did the allocate, we're just going to do a begin render. And now we have the option of saving this as well, rather than allocating it every time, which we might want to do too. Kind of up to us. Okay. Let's start. Oh, so is that may not be initialized as well, is the other thing, right? We didn't actually initialize that in our allocate, which I should do. There we go. So in here we want result in render equals false, so that we know we are not starting inside a render, certainly. Okay, so that's all fine. Now what we need to do is we need to actually start setting up our render group so that the render group will, you know, be able to display the bitmaps, be able to display the debug bitmaps. So what I want to do first is create an orthographic display. Now remember, there are two types of ways of transforming that we talked about on Handmade Hero: perspective, where things that are further away get smaller, and orthographic, where they don't, right? And so for our debug output, we just want things to be orthographic because we're just trying to make like a flat overlay on the screen. So when we initialize our debug render, we want to set an orthographic render group here so that we're just flat drawing to the screen with nothing weird happening, right? So if I set an orthographic display for the render group, we know that our screen has a particular size, right? I guess I don't know at this point whether the screen has actually been set, like the draw buffer itself has been set. It probably hasn't, so I think I want to use buffer directly there, like so, right? So we've got buffer width, buffer height, like so. And then we've got our meters to pixels. Meters to pixels, of course, is a little bit weird for these purposes because now we're not really thinking about any kind of real world units. But if we have a meter, how many pixels should it be? You know, we can pretty much pick an arbitrary thing. I don't know, let's say 100. Depends on how we want, how scaled we want our orthographic text display to actually be, right? But that's about it. So let's see what happens now. You can actually see right here, that's actually drawing to the 0, 0 location a bunch of the font stuff, right? So we're already seeing the results of that debug render. You can see that happens even before I launch a hero, right? So those are just the, you know, the sort of the letterings that we're talking about there. Okay, so the next thing that we want to do is actually get those displaying in a way that looks more like an actual usable font. The other thing that we don't really know about here is in terms of like what we want these actual sizes to be. I don't know. We'll have to think about that a little bit more. But let's press on a little bit first just so we can get more stuff happening before we try to make any of those decisions, right? So if I want to display this debug text line here, then what I want to do is I need some way, like this is just drawing them all at 0, 0. I need some way of actually sort of drawing them across on the screen, right? I need them to line up as letters. So I'm just going to introduce like a variable here at x, and that's just I'm going to move it like, you know, from left to right as I draw letters. Pretty straightforward, right? So if I put that in here and I just, you know, and I was to add something to the value here, then what I could do is say, okay, you know, how big are these guys, right? There's some kind of scale value. I don't know, they looked like way too big before. So I've got some kind of scale value here, right? And I'm just going to add whatever the scale value is. And, you know, if you figured that that scale value was somehow related to the bitmap, we'll figure out how much we should advance by in a second. So there we go. Hey, look, we're starting to get some debug text in there, so that's pretty good, right? But you know, it's in the center of the screen, and it being in the center of the screen is not really what we want, right? That doesn't help us super much. So what we would probably rather have is some way of like having it start to display itself like up in the corner. And furthermore, every time we get a new one, we'd want to move down to the next line, right? So what I'd like to do is say, oh, okay, I've got an @y variable as well. The @y variable I'll advance every time, you know, we get to a new line of debug text. Now, what you can tell though is that since this is just a function that renders a single line of debug text, I don't actually know when that happens, right? So at that point, we need some additional piece of information here. And hopefully you can kind of see where this is going in a second. We'd need another variable, right? We'd need an @y variable here to store whatever the y line is. And we would need that to actually reset itself every time we restart, every time we move to a new frame, right? Because otherwise it'll just move up right off the screen, and that that would be the end of it. But at the end of this, right, we would know, okay, we just got to move down a line, right? Actually, I guess since y goes up, we would move, we'd subtract to go downward, right? And so what we would need here is we need something like internal void, reset, or like debug reset, or something like that, right? And that would have to reset this at y equal to 0. Because if we don't do that, right, just so you can understand what I'm talking about here, if we don't do that, then it just runs off the bottom of the screen. We'll never see it again. Like, it's already gone before we even start. Before the even assets are loaded, it's gone, right? So we need something that's going to do that reset for us. And so we know, right, we know when that would be for us. And so we know, right, we know when that would be. We know that at the end, sort of when we're all done with everything and we do this end render, that we could do our reset here and it would clear everything out. Now, we could also do it at the beginning. It depends how we want to structure it. But there we go. Right? Now, we're getting closer. We got to move it up here. And also, you may notice that we get a bunch of Z's in here. The reason for that is we haven't put, this is kind of the fun part of about our asset matcher, is like, we don't have any lowercase letters. So it just thinks like, oh, I should just get the closest ASCII to that. It doesn't understand lowercase and capital letters. Maybe we should make it do so, and it knows to just get the uppercase version of something if it can't find the lowercase, right? But we're getting closer, right? We're getting closer to a font. So, okay, so probably, right, that scale value, it looks like it would need a little more spacing. It looks like maybe it needs something more like that in order for the line heights to be correct. There you can kind of see they're a little bit better, maybe just even a little bit more, something like this, right? And so there, that's a better looking debug display there. And so you know what? What the heck? We're having a little party here. Why don't we just go and have it include the lowercase letters too, right? Because right now we don't actually do the uppercase letters. So when we do the glyph extraction, I don't actually remember how we even did this. It's in here somewhere. Let's see, there it is, right? And so if we were doing this here, what I'd like to do is make it so that we have more stuff than just those. And so I'm going to go ahead and say we've got something like, U32 char range to like something like this. And then we do, you know what I'm talking about. This sort of thing. Right? Just making a little thing so I can output a bunch of ranges of characters. And we don't have any punctuation in there. But, we could look at the ASCII table and see. ASCII table. And if we look in here, right, the ASCII table is, of course, we've talked about it multiple times in the stream. It's basically a numeric table that says what the numbers are that correspond to the letters, right, that we care about. And so if you take a look in here, you can see that, like, we really don't care about most of this stuff. We don't need carriage returns or cancels or file separators or whatever these things are. Who knows? All we really need is this stuff over here. And so if you take a look at what these are, like 33, so, exclamation point. If you look from exclamation point, honestly, we probably just want everything that's in there all the way up to tilde. So what I probably could do is I probably could just not even bother and just do that, right? And that's probably fine. So let's give it a shot and see how that works. Hopefully it works okay. And so if I run test asset builder on this, presumably now we'll get a little more lettering. There we go. You can see it all nice there. And yeah, that's exactly what we wanted. Debug cycle counts. Oh, for space, we don't have space. Now, I don't know that we want to actually store a glyph for space because we know that it's not there. So I think probably what we want to do is actually just special case space because we don't need to ever actually draw it, right? So that seems like what we would want to do is something more like this. You know? And that way we, you know, actually get spaces in there properly. So there we go. So next thing's next. I think we'll be ready to start talking about font metrics because there's a bunch of things, as you've already seen, that we would want to fix if we were trying to make this font output actually look nice. So, what do we want to do here? First of all, like I said, got to move it up to the corner. So in order to move it up to the corner, I need some way of initializing at X and at Y to actually be something up in the corner. And that to me suggests that the debug reset wants to go up at the top, right? Because that's sort of where it would actually set that up, right? So somewhere in here it would do that. And maybe we include sort of, with that debug reset, we sort of include the orthographic in there, right? And so what that would do is it would take maybe that buffer width and height, right? So we'd have with it the width and the height, like so. And that would give us probably buffer width, buffer height, what the information is that we actually need to move things to the corner as well, right? Because if we do that orthographic, we now know that this is the width and height of the thing, and we know that this is the meters to pixels, right? So what we could do is we can set at Y, right? If we do meters to pixels, right? And in fact, when you think about it, meters to pixels, if we just set that to 1, meters is really not meters, it's world units, right? It's just the units we're passing in our stuff as, which happens to be meters everywhere, so that's why we call it meters to pixels. But we could say that we just wanted pixels to pixels, right? Wide, and we start at the center, do like minus half, seems, right? So if we said that we wanted something to be 1.0 high, right? Then what that means is it would be 1 pixel high. So I'm assuming that what that means is that our scale would now be drastically small. So we would actually need our scale to be much, much bigger than it was before, right? In order to... Okay. So now we've got roughly what I wanted happening, right? We've got it lined up where we want it, and we've got it printing out where we want it. But there's a ton of things that we don't have, that we want, right? So even before we talk about how to get like the numbers and stuff in here, we're ready to start talking about the font part. There's a number of things that you can see. I think I might leave them until tomorrow to point out, because since tomorrow is the day when we'll be addressing all of them, it seems a little weird for me to point them all out now. But point being, you can see like lowercase letters are as tall as capital letters. It's mono-spaced, so things that are like small, you know, have the same amount of spacing in between them. All sorts of stuff is not what we would want here. So even though we're getting a little bit further, there's a bunch of stuff that we want to do, and so tomorrow we'll start tackling those metrics a little more specifically. But hopefully now you've seen it's pretty straightforward how the debug text stuff would actually work, and off we go. Now there's another thing here, which is this is too slow for text at the moment. So we also want to think a little bit about the fact that calling this best match bitmap from every time is not perhaps the best idea, and so that's something we want to think about as well. But that's about it for today. I think we're just about out of time. So I'm going to go ahead and go to the Q&A because we're at a good stopping point, and tomorrow we can tackle all of the stuff we actually want to do to turn this stuff, which as you can see is just me writing the simplest possible thing and getting it to the point where it's working, turn this stuff into a more useful system. First of all, addressing some of that, but also all of these things in here, they're just these hard-coded constants. How do we start moving those into the font system so that we can get that information from the fonts, right? That's what we'll be doing tomorrow as the next step in our font metrics exploration. But I'll go ahead and go to the Q&A now. So if you have questions, now would be a great time. Robbie, hi Casey, question on the array you typed and pulled out again. U32 char brackets brackets 2. Is this an array with pairs of U32s? Yes, it is. I would have expected U32 brackets brackets. Oh, so in C, you were talking about this part right here. Then I realized I didn't have to do it. But in C, the way that you do an array, or a 2D array, right, is you keep stacking brackets on. In fact, you can do as many as you want, right? And the way that they work is it starts with the furthest one out. So for example, if I had this many, and I did something like this, right? Although you wouldn't have an array of 1, but you get the idea. So if I had something like this, what that means is the first array in the rightmost array index, right? This one right here is the one that increments in memory by the smallest amount. So effectively, if you were to look at these U32s, well, heck, I can just show you. So in here, I'm going to make this array, right? And then I'm going to do some stuff to it. So here, let's clear it. And then I'm going to do some addressing into it. Right? Okay. So I'm going to look at, in each case, I'm just going to go 1 unit along each of these guys. Right? Does that seem reasonable? And there we go. So in fact, I guess I could just do it this way. A, B, C, D, E, F. Right? So the way this works in C is this is the ones are closest together, is at the rightmost edge, and this is the ones that are furthest apart. That index will move you the furthest apart. So this is like saying I have an array of 7, arrays of 6, arrays of 5, arrays of 4, arrays of 3, arrays of 2, uint32s, all the way back to the other end, right? And so if I compile that guy down, and I set a breakpoint there, at the debug text line, right? We can see the array in memory happens like so. Oops, that didn't work. Come on. Why? Why will you not copy? Copy my value. Copy it. I do not know why you will not copy my value. Fine. OX3159A0. There you go. Happy now? Fantastic. All right. So if you look at me writing into this guy, this will write in an A to that location. I don't know why that did not show up. You did actually go there, did you not? Find A0. There's my A, right? Right there. So these are U32s. You know what? I should probably do them as U8s just so it's a little easier to see. There we go. All right. All right. One more time. How come I'm not, like, what's going on there? Does anyone know why it's doing that? Why I can't drag that value down? It's weird, right? So there's my A. And you can see that I have a 1 here. So if this was a 0, it would have put it right here. But because I said move 1, you know, on the lowest index, it moved it 1 byte over. So these are basically sequential, right? The lowest index is sequential. The next highest index up is going to be by however many this one was, right? So this is 2 bytes each. So moving 1 on this guy will move 2 bytes each time, right? So now we would expect it to move 2 bytes forward, which would be like over here, right? Make sense? Now this one's going to move 3 times 2 bytes forwards because it's moving 3 arrays of 2 forward. So that's going to move 6 forward just by an index of 1 here, right? 1, 2, 3, 4, 5, 6, right? And there you go. And then let's see. Where is this guy? This is 1. So this is going to be 5 arrays of 4 arrays of 3 arrays of 2. So that's 5 times 4 is 20, right? That is the one we're doing, right? Yeah. So 5 arrays of 4 is 20, times 3 is 60, times 2 is 120. I don't even want to count that. It's going to be down here somewhere, right? In theory. Let's see. 5 times 4 times 3 times 2 is 120. So where is the array at? It's at A0. That seems 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That doesn't seem right. Oh, I'm off by 1. Because of this thing. I'm off by 1. It's only the 4th one up. Okay, good. I was like, what's going on? So it's 4 times 3 times 2 is all it was. So that's it. 6 times 4 is 24. So that's totally fine. Right. Now it's the 120. That one should be down here. There we go. That could reasonably be 120. I could buy that. And then this one's going to be 6 times 5 times 4 times 3 times 2. So who even knows what that is? Something way down there. Right. So that's how those are read. In general, the way that you read a C declaration is pretty bizarre. It's always go as far right as you can first until you hit a parenthesis or the end. Go as far left as you can till you hit a parenthesis or the end. Repeat this process, right? I know what I said sounds weird, but that's what it is. It's go as far right as you can until you hit that. Go as far left as you can until you hit that, right? That's how you read them. So if I say array this, then I have, well, we'll get things a little simpler here. If I say array that, I've got an array of 3 arrays of 2, and now I've hit the end. There's nothing left. So imagine there's an imaginary parentheses at the end. So an array of 3, arrays of 2. Then I start over going to the left, U8s. So this is an array of 3 arrays of 2 U8s, right? Start at the name, go right, right, can't go right anymore, back to where I was, go to the left, done. These can get very complicated, and you can make all kinds of ridiculous stuff. For example, what is this? Anybody know? Well, it's an array of 3 arrays of 2, got the end, pointers to U8s, right? So this is an array of 3 arrays of 2 pointers to U8s, right? But what is that? Anybody know? Just do what I said. Start in the name. It's, array, or I should say something like foo. Foo is. So foo is it an array? Not yet. Foo is, I hit a parentheses. So now I go backwards. Foo is a pointer, right? Now I hit another parentheses. So now I go to the right again. To an array of 3, keep going to the right, array of 2, and I hit the end, go back to the beginning, U8s. Right? You want to make it more complicated? Go ahead and make it more complicated. Let's parenthesize this. Right? In fact, we can make it even more ridiculous. How about that? How about this? Right? Now we've got foo is, hit the right paren, go to the left, got the pointer. Oops. Come back. What just happened? What just happened? Okay, there we go. Foo is, go to the right, hit the paren, go to the left. Foo is a pointer. Hit this paren, go to the right, to an array of 3, hit the paren, go to the left, hit the paren again. I guess we have a redundant set of parentheses there. That pair, I guess, doesn't really need to be there. You could get rid of that, right? To array of 3, hit the right paren, go back to the U8, 3 U8s, And this whole thing is an array of 2. Right? There's 2 of that whole thing. So 2 is an array of 2 pointers to arrays of 3 U8s. Who knows? Why would you have that? I don't know. But you can have it if you want it, right? So that's, you know, that's what that is. Happy birthday. Foo undeclared identifier. What are you talking about? Why are you grumpy about that? Pointer to an array of 3, array of 2. Why don't you like that? I feel like I should be able to do that. Maybe I can't. I feel like I should be able to do that. Maybe I actually can't. This is not a variable declaration style I would ever use, but foo is a pointer to an array of 3 U8s. I guess you're not actually, now that I think about it, that's actually not legal. You can read it, but you can't actually write it. Because that completes the definition already, and you can't really add the array of 2 in there. So if you wanted to do the thing that I said, you'd actually have to put the 2 there, if that makes sense, I think. So that it would be like foo is an array of 2 pointers to arrays of 3 U8s, right? Like that. That's the only way you could actually do that declaration. Because once you actually wrap it up, you're not really allowed to then make that be a 3 thing again. Not sure why. I guess that's just because the way the C parser is written, it doesn't have the ability to take that for whatever reason, right? It's like it can't handle you wrapping the type up in there because array subscripts in the parser have to be parsed before the final type of the thing. So when you actually do that, I assume you kind of would need another type there, right? Something like that. And of course you can't, that doesn't actually work. So they pretty much only allow you to actually put the array subscript in there. I don't know how I got off on this tangent, but point being, that's how to read C declarations. If that. Cuber Caleb, do programmers actually use that crazy array semantics that you just said? No. As evidenced by the fact that I accidentally constructed something that you can't even actually type in C. I never type anything even remotely that complicated. It's just I happened to remember how to generally read those because sometimes you have to. But I mean, to say the very least, your goal should be to never have to know that stuff I just said. Because if you actually, it's more for reading other people's code when they've done something crazy. I never, you know, hopefully you never do that. Use some type defs or something if you have to. Insofar as you didn't answer the how about a 2D array of function pointers might have been why a few of those variants didn't compile because it thought you were declaring a function pointer array, star foo. Maybe. Around how many more episodes until you the switch from software rendering to hardware rendering? I don't know that we'll ever switch to hardware rendering until like the end. I mean, I would rather always do software rendering. So it's only for speed purposes that we would do the other one. Right? Can you rotate and This is, well, really, this is kind of like a little bit of a detour, you might say, that we're on, where I'm kind of like, I wanted us to have some debug code, and I kind of got into it a little bit. And so for the past few days, we've been sort of like working on cleaning up the debug presentation so that we could do some fancier things with it. And we sort of did a little bit of that yesterday. We kind of cleared out a bunch of like global stuff and like consolidated the state. And so today, what I'd like to do on Handmade Hero is I'd like to go through and add a little bit more of a UI story. So we kind of set the stage for that yesterday a little bit. And what I'd like to do today is kind of push through that and maybe get us some things like some buttons we can interact with or something like that. Again, so we can do stuff like quickly have access to turning off or on the profile or other things like that. And I'm not sure exactly how we want to do it. So we're kind of just going to push on it a little bit and see what happens. Now I have some ideas. I was kind of thinking about something that I kind of wanted to try potentially. That's sort of a little ridiculous, but sometimes ridiculous things are the best things, right? It's hard to know sometimes what it's hard to know. It is hard to know sometimes how these things should go. So I might try something like epically ridiculous, like something so ridiculous that it just has no right working. And then if it does work, we'll just be like, I do not know how that happened. But, you know, we're happy that it did, or something like that. I'm not sure. So yeah, so we'll see again, and I don't really know. There's some things about the C++ preprocessor that I suspect that one of the things I would like to do probably is just not possible to do. But I don't know. So, you know, we'll see. All right. So, let's go ahead and get started here. Today, I think we probably won't get into some of the crazier stuff that I was talking about. That'll probably come maybe tomorrow or the next day. For right now, it's day 191. We're going to be doing some coding. We're going to be probably doing a little bit of UI coding. So if you want to follow along with that, unpack day 190 source code into a directory somewhere. That's what I'm starting with. Again, that's if you pre-order the game on handmadehero.org. Let's go ahead over to the code itself and see where we left off. We had just done some stuff with the profile window, and we basically made it so that we could make a little, we could just kind of control the size of the profile window there, right? And that was just sort of a beginning of sort of getting rectangles in and a little bit of that conceptualization there. And that's all good, and it's kind of running in there. So what I'd like to do now is I'd like to sort of continue pushing down that direction and say, let's try to get something where now we have some concept of, like, you know, various sort of, I don't know if you want to call them widgets or whatever they are, some sort of concept of like pieces of stuff that we want to display, like these things, so that they can be turned on and off, and, you know, using some kind of a control, some kind of a thing we could click on, or a, you know, a menu or something like that. So some sort of a thing like that that we can use to sort of get pieces of the debug code like this in a state where they're not bothering us, right? They're not kind of getting in our way when we don't need them. So we can turn them on, we can turn them off, and that sort of thing, right? So that's what I'd like to start doing. Again, very, very simple, nothing particularly crazy going on here, but that's what I would like to have happen. I'd like to get us into that position going forwards. And again, yesterday we also made sure our loop live code editing worked with the debug stuff. So I believe all of that stuff should work fine. I should also check to see whether our L key stuff works. With the debug, and it does look like it works pretty fine. So that's actually kind of nice too, because it means that we will have the ability to go in there, and if we have kind of bugs that are difficult to repro, if we can get them into a loop, we can look at the perf stuff in there as well. Perhaps even freeze that stuff. For all I know, I'm not sure if that'll actually work or not, though. Probably not. Yeah, I guess we can't. Well, yeah, that's right. We can't. We'd have to sort of think about how we wanted to have that happen, because if we bring that sort of loop live code editing stuff in a little more properly, we're going to have an interesting dichotomy there, which is that the recording stuff, again, one of the important things when you're coding anything, and I try to say this oftentimes, is and it's kind of evolved a little bit in Handmade Hero. I think before Handmade Hero, I hadn't really crystallize so much exactly what it is I do when I code, which again was one of the big reasons for Handmade Heroes. I just want to kind of show how do I actually get things done, so that other people who are like, I would like to see how someone gets thing X done, they can at least see how I get it done, which may not be how other people get it done, or may not even be a great way to get it done, but it is how I get it done. And that is, in this particular case, and in pretty much all throughout Handmade Hero, I always start at the place where I know what to do, and I work towards the place I don't know, right? And a lot of times I would say, like, write the usage code first or things like that, but it is true that if I don't know the usage code, then I actually, but I do know the implementation code, I start at the implementation code. Like, what I actually do is I start at the place that is certain, and I move towards the place that is uncertain. It seems like that's a much truer way to state how I actually program than trying to boil it down to a specific rule, which won't necessarily be true in all cases. So it seems like I do tend to start with, like, what do I know has to happen? And let's make that. Because that's the thing I'm most likely to get right. And then let me move towards the thing where I'm not really sure what it does. Because by going from something I do know to something I don't know, I advance sort of, like, I get closer to what I don't know with things I do know and make that jump easier to make conceptually. And so that's exactly what I'm going to do here. If I want to make a radial menu and all this stuff, and I've got, I don't know, UI, and you pick things and it turns things on and off, that's a lot of stuff to think about, right? That's a lot of stuff to consider. And a lot of times people will rat hole, they'll kind of go down and think about it and draw pictures and diagrams and make a UML thing or C++ classes, but they don't really know, and it's kind of, and that doesn't help. It just complicates matters, right? Instead, what I like to do, like I said, is start with something you know. We know how to draw stuff. Let's draw the radial menu. Let's just figure out how to draw the darn thing, right? I'm just going to say, we've got a function. I'm going to put it in here. I don't even necessarily care what it's called. I'm just going to say draw radial menu. I don't even know if this should be a function or not. I just want a scratch pad. I just want something to call into where I'm going to get this render group, right, in here. And I want to also have, I guess, my debug state probably. And I'm just going to say in there, I would like to draw myself some kind of a menu. And you know what? Let's not even say radial menu, because what I really want is just the debug, the debug main menu. It's just it's the thing that comes up when you hit that right mouse button. And then I'm just going to call it, and I'm going to call it all the time. So I'm not even going to think about the UI. The UI is not even on the table at this point. We're just going to straight up do whatever comes to mind for drawing the menu, assuming it's always on the screen. And we'll work backwards from there. So the first thing I need to do is I need some items, right? So again, not going to think about it at all. I'm just going to say I have some menu items. I'm going to pretend I just have them right here. I don't know how many menu items I have. I've got some. Okay. So I've got menu items, and in the menu items are just going to be some things that I could select, right? What are the menu items? Toggle profile or output. I don't know, graph. Toggle profile graph. Sounds like a good menu item to me, certainly, right? What else might I want to do? We had that frame rate counter. Toggle frame rate counter, right? That was the thing that was up there. Let's see, loop, mark loop point, right? Of the, if I want to do loop live code editing or something like that. Draw entity bounds, right? Something like that. Draw world chunk bounds, or toggle world chunk bounds. Something like that. So I have no idea if those are things we actually want to do. All I know is I need some menu items, so I'm making some menu items. Now we have them, and we are good to go. All right, so if I need to draw menu items, well, I'm going to have to loop over the menu items. That seems like a no-brainer. So here's my menu item index. Right? And then I can get that menu item name, or maybe just text, right? Text of the menu item, one might say. And then we've got menu items plus menu item index. Yeah. So if that's what I've got for the text, I just need to know where I would display that text, right? Because I have ways of displaying text I've got a thing here which is just debug text out at, right? So that's all good. So if I go in here and I do debug text out at, oops. I know that I've got a point and a string. I just need to know, like, I'm going to put the string at this particular point. So all I have to do there is say, okay, I know the text. That's the text I want to show for my button. So all I really need to know now is where is the actual button? Like, what's the location of it? And so if you think about, if I wanted to do something where it's like a radial menu where they're kind of, like I said, around a circle around the point or something like that, right, here we go, day 191. If we wanted to do some kind of a radial menu so that I'm like the mouse is here and you go down and you get something like this and it's got like the menu options, you know, that kind of come up in this sort of fashion, you know, like that. If that's the sort of thing I'm doing, well, you know, we know what the points are. The points are just going to be going around the circle, going around like basically the circle. So whatever the radius of this sort of like radial menu is, however far the distance should be, that's certainly parameterizable. That'd be like an R value. And then we would know that however many of these guys we have, you know, we've got some kind of an N here, which is a number of menu items. I want to make it so that I'm going to divide the circle into that many things, right? So if I have, you know, let's say I've got here 1, 2, 3, 4, 5, 6, 7, 8, right, of these that I want to lay out. Well, that means I need to make, you know, 1, 2, 3, 4, 5, 6, 7, 8 segments of the circle. So I should be able to divide the entire, you know, I should be able to divide the entire tau, right, by 8, and that's how much to advance the angle by as I go. And then, of course, I can always get the arm of the circle, as we talked about before, by just using the cosine of the angle and the sine of the angle. The cosine, of course, gives us the x-coordinate. The sine gives us the y-coordinate as we go around the circle. And multiplying these guys by the radius will move us out from the unit circle out to the outer circle where we want to be. So I should be able to get the point to start the text at there. Now, we have an additional concern if we want to make this menu look nice, and that is that we want to probably center the text around that point, whereas what we've got right now is something that starts at that point like as a baseline and does that. So our circle is going to be wonky and it's going to look kind of like that at first. But that's not the end of the world. That's totally fine to get it going, and then we'll look at how we might fix the sort of centering issue as a separate thing. All right, so I'm going to do exactly what I just said. Again, really, really straightforward. So if I do that, you can see that I've now got my radial menu. Again, like I said, it's not really centered properly, I don't believe. Although, actually, it kind of looks like it is. Did we actually do... But that's weird. That doesn't seem like... I gotta say, nothing particularly odd happening here, but, you know, I should be able to do this. Sherlock93, can you explain a bit more on the closure stuff and how to do it in C? I didn't quite understand it. So the closure stuff is just... if I have something where I'm going to say... it's a good example. So let's say I have something like do complex iteration over things, you know? And I'm going to do some iteration where I walk a tree. In fact, you know what? You don't even have to guess. I'll just load up some actual handmade hero code that actually has to do this. And then you should be able to see what I'm talking about. Okay. So do you see this thing here? Get world chunk, for example. So get world chunk, what it does is it looks through a list. And it figures out which world chunk it wants by comparing each thing. You know, it first figures out the hash, it goes into the right slot in the hash, it then goes through and compares and tries to find a particular one. If it didn't find one, it will like get a new one and all this other stuff, right? There's all these things that it does. And so if you wanted to write something now, where you were like, I want to write something that just does something to everything in this list or something like that. Or, you know, something that maybe, you know what? I'm not even sure that's the best one. That might not be the best one to illustrate it because there's a slight twinge to that one that makes it not as good. What's the best place in him? Ah, I got it. I got it. So, at least I think I got it. Okay. So, let's say we were to take something like this. So here is a very complicated thing. Draw a rectangle slowly, right? Here's a very complicated function. It does a ton of stuff. It then has a bunch of code inside where it basically says, okay, it does a bunch of work to figure out all the pixels and whether the pixels were highlighted and all this stuff. And then inside it has what is essentially a shader. It has the code that's like, for a given pixel, I want to compute what the color should be. How do I do that? And that's all in here. Now, if we wanted to make multiple shaders, right? The logical way you would do this is you would have, in your programming language, a way to say, oh, by the way, I want you to just have a way for me to say, all of this external iteration code, just make that code be a reusable chunk, and I just want to replace this part here. So I'm going to stick something in here that's like, do the stuff, semicolon, and then I want to be able to call, quote unquote, this function, and tell you what to replace do the stuff with. And so that it can access all of this information, right? That's like the most basic use. That's not even a closure. That's just a macro almost, right? But oftentimes, that thing itself wants to have access to a separate stack frame. So it wants to have access to variables that are not necessarily known by this function. So for example, let's say that one of these is the normal mapping thing, and it needs access to the lighting environment. Whereas the other way we might call it doesn't do any lighting, so it doesn't need access to that. So what we would want to do is pass in not just the code to execute, but also a little stack frame, a little set of data that goes with it that it can just go ahead and do, right? And so, you know, other programming languages have a variety of things like closures, which allow you to encapsulate the data that's referenced by something, by a piece of code, into itself to be passed through to somebody else where they can do stuff with it, and then it can come back to you and have done the things that it needs to do in your stack frame, right? It allows you to kind of mix these stack frames together in a very useful way. It allows that, but more importantly, it is also just even separate from the closure part of it, the fact that you can sort of pass code into something and have that code execute inside another piece of code is something that C can't do. And C++ recently added lambdas, which kind of allow you to do some of that stuff. And that is the thing that I was saying we don't have if we don't want to go down the C++ nightmare route. So what I did is sort of the poor man's version of that. What I did is say, okay, let's just put in that place where we would, which right here, in that place where we would have wanted to pass in the thing to do, we'll actually just put all the code in there and just have a variable that tells us which one to do. And since branches are relatively cheap, it probably isn't that bad, right? So that's what we did. And of course, we don't have full closures, so these things cannot do anything like have data that comes through that only they know about, like the thing I was saying before. They can't really talk to someone else's stack frame or do any of the convenient stuff like that we might want. But like I said, for a poor man's version, it's totally usable. Hopefully that makes some sense. Hopefully there's some better editor to use soon. Maybe if Mr. Fourth Dimension gets 4Coder up to speed, we can just be using that instead. But yeah. Elvin, oftentimes when using someone else's API engine, you end up having to fight with it to have it do what you want from it. Do you think that is a sign that one should leave that API and try another, write his own, instead of fighting all the time? It's a tough question. the answer is that it depends. A lot of times that's true. You know, if you're using Unity or something, you're probably going to spend a lot of your time fighting with it or whatever, and it's just like you're making a trade-off of basically saying, yeah, this thing is not going to be architected to do what I want to do. It's just this kind of thing that is whatever it is, and I'm rolling the dice and saying that I bet that I can save time in the long run by using Unity because of all the code they've written for me, versus all of the aggravation and time I'm going to have to spend trying to get it to do certain things that it's doing wrong or that doesn't do right for my game. And you're making that judgment call, right? So sometimes I would say, no, it doesn't mean you should switch, right? It doesn't mean you shouldn't use Unity, because the total time to develop the game may still be shorter if you use Unity than if you don't, right? Especially if you're not a very experienced programmer or something like that, right? So sometimes you have to think of the fighting as the cost of not having to write the code yourself, and it may end up being a win, right? Again, it all depends. Other times, if you're really fighting with it and it's not working, it may be the fact that, like, okay, Unity just can't do this. You're going to end up basically rewriting almost the whole thing yourself anyway in C# here or whatever, just to work around all the things that it doesn't do right that you need it to do. And then, yeah, it was a bad idea to, like, keep using that thing, you know? And unfortunately, that's a really very tough decision, especially for a novice game developer to make. Knowing which one of those is going to be true is very, very hard. And it's closely related to another similar decision, which is what thing to use, library, engine, right? For example, you're a novice game developer, you don't have the skills to make an engine. Should you use Unreal Engine or Unity, right? Or Game Maker? And, you know, unless you've built things in all three, it's very hard to know the answer to that question, right? Because, yeah, you will fight. All three of those you will fight because things that you will want to do, it will not do in the way you want to do them or the way that your game needs them done. That will happen. Which one of them will be the least fighting, right? And so it's definitely the case that those are all very hard decisions. Fighting is definitely a sign that the thing doesn't do what you want it to do the way you want it to do it, but that doesn't mean you need to stop. It means you just need to be aware of it and understand that everything is a cost-benefit trade-off. And if you start to sense that writing maybe a particular component from scratch or a whole thing from scratch is going to be the better way to go, then you need to do that, right? And that's, again, unfortunately, the kind of thing that's very difficult for a novice programmer to make, because it's about experience in a lot of sense, and there's really, without being burned a few times and seeing how you get burned, it's oftentimes hard to know just how hot the pan is, right? So that's an issue, certainly. What I would say and this probably doesn't go for any of those things, because in those cases, I think most of the time if you're fighting, it's probably because it's janky. There are certain cases, very limited cases, but certain cases, where you're fighting the API because you actually don't know what you're doing. And an example for this, of this is probably like when I was, say, 20 years old. If you had shown me the I/O completion ports API in Windows, I probably would have said it was stupid. And I would have had to fight with it to get it to do what I wanted it to do. Nowadays, I think the I/O completion port API is like pretty darn close to perfect. And that is just because I get how a certain type of code should be written now, and I get what it needs to do to be performant, and I get what it needs to do to be properly multi-threaded. And until you know all of that stuff, a very well-designed API may actually seem stupid or confusing or that it has something wrong with it, but it's actually you who are incorrect. That happens fairly rarely, but once in a while it does happen. And, you know, I suppose it's not a surprise that the I/O completion port API is an example of something like that, because that was designed by some really, really great operating system guys, like back in the Dave Cutler days. So, you know. Cuber Caleb, wait, isn't 4Coder already better than Emacs? Some of it is, the like refresh time and some of the stuff is, but there's a bunch of things in Emacs that I need that doesn't have yet. And so until it's up to that level of functionality, I can't switch. Cuber Caleb, can you go into detail on IO completion ports since you brought that up? No, because we're out of time, and trying to explain why IO completion ports are a good API would take a long time. So that's probably a topic that's better saved for a different day. So if I run things here, you can see that we kind of had a situation where we started making a little bit of a debug output, thing here. And some of these things, these debug output things, are like, stuff I can expand or collapse like this, right? And we haven't done anything particularly fancy, certainly, but that's, where we were at. And some of these things even were like different kinds. So like there was a 50 of value, and we wanted to make something where we could start interacting with that value. And where we left it, if I click on this, right, it just goes to an assertion here because we haven't implemented any way to interact with those. Because all we had was stuff where you could interact with by a click. Either it could like negate a Boolean, or it could expand a tree view element of a group. But if it was any other kind of item that might have like, a value range to it, we didn't really have any way of interacting with that thing. And so if the reason for that, of course, right, is because we haven't talked about at all about how we might do user processing or any of that sort of stuff. So all we just had was just the click, and that's all we could do. So what I'd like to do, again, is like talk a little bit about the structure here and then start to implement some things so that we can have a more coherent concept of how we might deal with interaction in the debug system. And we won't go too far with it because, again, it's really not going to be something that's going to be in the game. So we don't, it's probably not even something that I might even spend any time on in reality here. But because this is an educational stream, I thought it was a good opportunity to talk about this a little bit. And I think it's something people should kind of have a reasonable understanding of, right? So here we are. Here's day 196. And this is sort of like UI input processing. All right. So you've seen me do some very rudimentary input processing. And it's the kind of input processing that a lot of people associated with the I am GUI style stuff, right? Which I am constantly asked about. And in general, what I mean by the type of thing people associate with it is they often associate I am GUI style processing with like single execution model, I guess I would say. Right? And what that means is if I have something like a checkbox, and I've got a thing next to that checkbox, and what I'm going to do with this checkbox is I click on the checkbox and it checks it, and I click on it again and it like unchecks it or something like that, right? That's the interaction model I have. Then typically what ends up happening is in I am GUI, you will see something where they'll do like, you know, or they won't even do if checkbox, I guess if it's a checkbox, they'll just call checkbox, right? And then inside this checkbox routine, it will do something where it decides, you know, is the mouse in here and has it clicked? And if it has or not, it'll like toggle the check on or off, right? Then that's the most basic, the most straightforward way that you could possibly implement this thing. You know what I mean? Now, there's a problem with this way of thinking about things. And that is that it makes it rather difficult to decouple the way in which things work with, how should I say this? It makes it very difficult to decouple the interactions from the specific thing that is on the screen, right? So for example, if what I wanted to do instead was I had some kind of a selection paradigm. So I wanted to like select this thing. And maybe I had like a toolbox over here that was like my checkbox tool, and I had my selection arrow tool. And if I was on the arrow tool, when I clicked on this, it should select it. And when I had my checkbox tool, right, I wanted to like check it or whatever, you know? Then what that means is every possible tool that I might want to implement or every possible behavior that I might want to implement has to get stuffed inside this checkbox routine. Which means that the person who implements the checkbox routine has to be the person who knows everything that might ever actually occur here, right? Because the interaction cannot be written outside of the thing that it actually, outside of this actual call. Everything kind of has to happen inside there, right? And so I just wanted to point that out. That is sort of the thing that you've seen me do so far. And I don't consider that I am GUI at all. I just consider that to be one very simple way of implementing interaction processing that really has nothing to do with whether you're immediate mode or not. And specifically, the reason that I say that is because I am GUI, the immediate mode part of I am GUI, is only talking about the fact that these things are announced by the code, and it does not talk about the fact that the thing that is announced had to be checkbox. Right? Instead, what could have been announced here was some generic thing that's just saying, like, I have a Boolean, right? It has this information about it, and I'm not going to say anything about how I want you to process it as a UI element. I may just be putting these things into a batch, right, as part of the IAM pass-through that buffers up all the information about what ended up on the screen, and then it could have a totally separate set of code where people have implemented different tools, which will then scan through this batch and do things. Right? Because there's nothing inherent about the immediate mode nature of the UI that requires you to not do this. Right? The immediate mode nature is just about the fact that the calling code, it doesn't have to save like a pointer. It doesn't have to call a create function to create some kind of a widget. It just announces the things that it has. And it just does them in a pass and it's done. Now, what it announces, on the other hand, is totally up to it. And again, that's one of the big reasons I say, like, most people don't seem to conceptualize IMGUI the way that I had intended. Not that I really care, but that's just part of it. So what I'm going to kind of show here as we develop our debug UI a little bit more, I'm going to try to show you a little bit of how you might structure your code in such a way as to avoid this kind of a thing. Just because I'm assuming that everyone could find reference to how you do this, and I've already shown how to do it a little bit in the code. So for example, if we go into here to handmade debug, oops. So, you know, we've got a pretty obvious situation here. This is an example. We've got these debug profile things on the screen that we had been printing out. And if you press the left mouse button, it would just take whichever one you were over, right? And we've got these debug profile things on the screen that we had been printing out. And if you press the left mouse button, it would just take whichever one you were over, right? And it would do an operation on that, right? Does that make sense? And so if you look at how this code is structured, it's very immediate mode, meaning this thing right here goes through all the counters. It does a bunch of operations on those counters. But all it does when it does that processing is remember who it would have been interacting with, right? Like, who is the person that it's interacting with? Then at the end, at the very end, it goes, okay, now I'm going to just do whatever I want to do UI-wise, and I'm going to use whatever came out of the immediate mode pass as the information about who to do it to. And what you can see, if like what I'm trying to say, like I said kind of here, when I was talking about this, what you can see there is this is totally decoupled from the part where you're actually doing that processing. The thing that knows what to do with the UI element is a completely different part of the code than the part that actually drew it on the screen and recorded the fact that it was there. And that's the way I tend to like to structure my UIs, because with that structure, it affords you a lot more possibilities for writing things that work cross UI element or in a broader sense with the UI elements than if it is baked directly into the operation at the time. Because we could have done that. Remember, I could have done what was pressed. I could have done that right here, right? Instead of storing the hot record, I could have done that right here, but I chose not to. And by comparison, I think we did it the other way in one of these other ones here. I can't remember though. Let's see here. No, okay, I guess looks like I did it. Looks like I did it that way in both cases. I did the debug state hot variable thing here as well. All right, so that's okay. So I think it was only when we had it baked in here, which we had when we had it in here before. I think we did at one point. I think that was the only time that I was doing it kind of in the older, in the sort of like more direct way, which I don't super love, right? Okay. So that's the way that I'm going to continue pursuing to do things, but I'm going to take it a slight step further right now that we've got this. And what I'd like to do is I'd like to have a notion of the place in which these operations occur. And so, like I was saying, my first thought when I said it was premature, I was premature to call it premature. Let's be honest, because I do actually want it this way. So I would like to be able to say, like, okay, I know that I'm doing an interaction, so now there's just some code in the movement thing that says what I'm going to do in that case, right? And that's, you know, that's how that goes. So then I've got one in here, which when we're doing the drag value, it does that. The rest of these guys don't actually care. In fact, I could almost say that they don't actually do anything at the moment. And then I've got sort of the other things that might happen at the end of that interaction at the moment. Something like this. Then what I'd like to do out here is say, like, okay, could you explain the difference between how our IAM GUI is often implemented and how you think it should work again? It went a bit fast for me. So this is just one of the things, one of the many things. But like one way is the way that I wrote it here in the debug one, right? Which is to say that the interaction code is separate from the pass that does the drawing. So these are like out here. This is the drawing, right? Debug drawing menu. It doesn't do any interaction itself. Instead, all of the interaction is deferred to later by using the hit testing that happened in the IAM pass. Later on, somebody will actually do the interactions. And basically, it's splitting those two things apart that I think was the part that I was trying to talk about. So we could have shoved these in there, right? We could have shoved these directly into here. When we do our is in rectangle, we could have done it here. And I just don't think that's a very good place to do it because I feel like it makes it harder to decouple and it's harder to keep the code organized with the parts of the code that you want it to be organized with. It's, in some sense, it's just a stupid artifact of the way that you know, procedural stuff works. But I just find that I like to pull those two things out. But that was the only part I was trying to elaborate on. Let's see. Saber 173. You know, what can I say? All right, so I'm going to go ahead and open up Emacs here, just so we have our source code at hand in the editor as well. And then I'm basically going to take a second to talk about and think about how I want to go about verifying that this code works. So we've got a lot of moving parts here. There's a lot of things that we have to think about. First of all, when we come through it the first time, we fill the entire buffer, basically to give it something to play. And then we're going to go ahead and kick that off. So that means as soon as we fill the buffer the first time through this, then we kick off Okay, I am going to go ahead and jump right here. When we ask for direct sound create, basically we're calling direct sound create, and direct sound create is going to give us back an object with that vtable in it. So You'll notice we don't have to ask, we don't have to use getProcAddress to get the rest of the functions we're going to call. Instead, we're just calling them off of the actual object that we got back, and basically the vtable that is in that object is the thing that is actually allowing us to get to these other functions. And just to be a little more explicit, you might say, well, where is that vtable in memory? Well, the vtable got mapped into memory when we loaded the DLL. So the DLL itself had the vtable in it. When it got loaded, we are actually pointing to, when we get back our handle to the struct, or I should say the direct sound object, since we're, whether it's a struct or a class, who knows how they declared it internally. It doesn't matter for our purposes at all. Structs and classes are the same. Anyway, point being, when we get back that handle to the direct sound, it basically has a pointer to a vtable that is inside the direct sound DLL, and we will basically just be calling through that jump table. So every time we make a call, it'll look up in there, it'll grab out that thing, and there it'll go. And we can even, if you want to, oh, I got to save my file. If you want to, we can go ahead and even take a look at that happening. If I open up the debugger here, again, everything gets translated to CPU. It doesn't matter what language you program in. The CPU has to do everything. So no matter how fancy stuff looks in a language, basically you are always going to end up having to have the CPU do whatever work is necessary to have that happen. Languages make things sometimes simpler for the programmer. They do not make things any simpler for the CPU. That is just how that works. So basically you can take a look at this here. Let's see here. So you'll notice this is the assembly language for this call, and you will notice right here, this is the part that we're looking at. So normally, when we call a function, I'll just show you another example here actually, just to make it a little clearer. So normally if we went down here, and let's look at a function that we were actually, that we had implemented ourselves, right? This is a function that we had implemented ourselves. So if I go ahead and I go to the disassembly here, you will notice that basically what gets outputted is essentially a direct call to the address of that function. And what basically happened was the linker, when it linked us up, it basically said, look, that is where the function is. So that is the address I'm going to output, and the call is just a direct call to a constant address. That's what happens. There's nothing fancy going on, and it's one thing. When we call into it, then we're in the function. That's it, right? That's what happens. Now, in C++, every time you use a virtual function, you are basically incurring more overhead than that. What you are actually doing is you are going in here, and you can see that this is the call site. This is the place where we're actually going to call that set cooperative level. And as you can see, it cannot insert an actual address. It has to basically insert a call to an address that it loads. And you can see that happening right here, basically. You can see that it moving into RAX. It's basically getting the vtable pointer, it's loading in that function. This is doing the pushes for the actual, I think the actual parameters and stuff that we want. But this is actually doing a call off of RAX, which got loaded up here. So you can see that it's actually doing work to load something in. First it's loading off the RSP, then it's going ahead and actually loading off of that, which is the double indirection. Like I said, it's loading a pointer and then loading a pointer off the pointer. Excuse me. And then finally it's calling one more indirection. It's basically calling, to be more explicit, it's loading in the direct sound. it's loading the vtable pointer out of the direct sound, then it's loading the actual address out of that vtable because it knows this is the address, I believe. I am not the best person at assembly language. I've never written a compiler that outputs C++ assembly language, so I'm just basically assuming that this is roughly what it has to do. Now, maybe if we were in optimized mode, it could get this a little simpler or something like that, but basically that is the idea. So you got to load the pointer to the object, you got to load the pointer to the vtable, then you got to load the function pointer out of that, and finally, you can go ahead and call it. So that's what's going on there, if that makes sense. Hopefully that's clear to everyone. It's not particularly complicated, and you don't really have to understand it, because we are not going to be using anything like that in our code, but that is what happens in C++, and that is what happens in COM as well. So that's what's happening in here. We're getting back one of those. We are basically asking direct sound for a handle to the primary buffer, and that primary buffer we are using to set the output format for our sound, which we set to be stereo, 2 channels, 16 bits per sample, which is good, and excuse me. Again, sorry, I'm so sick. And we are also saying that we essentially want it to be 48 kilohertz audio, which I picked basically because I think one time I asked Jeff Roberts, who of course was the guy who maintained the Miles sound system for a very long time, what was the most common native format for sound output, and he said 48 kilohertz, so that's what I'm going with. But you could pick 44.1 as well, CD quality audio. You know that all sound cards support that as well. Pretty much has to, I think. It was just a question of whether they resample it or what they do to it. So anyway, we then open our own buffer here, and that is what we're going to talk about right now. We open a buffer called the secondary buffer, which is the buffer that we can actually write into. We can't write into the primary buffer. Those days are over. We have to write into the secondary buffer. That's the way that's supposed to work now. And basically the kernel will sort of take all the people who are writing the secondary buffers, mix them together, and output them to the sound card. We no longer get direct write privileges to the sound card. Kind of like we no longer have direct write privileges to the graphics card. It all kind of gets mitigated. It all goes through Windows. I guess if you use something like Mantle, maybe you can, but assuming that you're going through the Windows standard APIs, you don't get direct access anymore. It's just not how it works. So in here, what we basically want to do is we want to keep this buffer pointer around. This is basically the thing that we're going to use all the time to write to the sound buffer. So I'm going to basically elevate that out, this secondary buffer. I'm going to elevate that out to our globals. Again, I'm not sure that that's going to stay there necessarily because, like I said, I don't like to have too many global variables. In a platform layer, it's usually not that big a deal, actually, because you're kind of really isolated in the code here, and you kind of have looked at it all. It's not that big a deal, but at the same time, you always want to be aware of it because a global variable is something that anyone can modify, and sometimes that creates a little bit of a stringiness in your code. So be aware of what you make global. Don't do it willy-nilly. Make sure you understand why it's global and that it should stay global and that there's only going to be one of them. And if any of those things aren't true, don't do it. All right, so we're going to actually create that buffer globally here. And then once we get that buffer, we will be able to output sound from now on. So in order to output sound, basically I'm going to do something extremely simple. I am just going to ask where the right pointer is, and I am going to fill in some memory with the sound. And now sound is a little bit wonky, certainly. It's a good question what we're going to put in there if we're not loading anything yet, because I wanted to wait for, I'm going to show you how to load WAV files later so that we'll be able to play sound. But to get something working, first off, I think I'm going to use a good old square wave, something like that, so that we can just hear. It's going to be an awful sound, certainly, but if we take a look here, you can see basically we have a square wave. It's got a pretty reasonable graph here. These are the basic kinds of waves that you can output that are really simple to code. Obviously, there's a sine wave, there's a square wave, triangle wave, sawtooth, and they just look like this. You can see square is probably the simplest to code. All it is just a high signal high positive signal, followed by a low negative signal, and nothing in between. So it's just just a full-on oscillation like that. And that's about it. So I think basically that's all I'm going to try and dump into this buffer. So basically we're in our loop here, right? One of the things we do in our loop is we get the input. Then another thing we do is we render that weird gradient. So right here after the gradient, I am going to go ahead and try to lock that buffer. So I am going to go ahead and do direct sound output test right here just to see if we have anything working. Now, in order to do that, basically what we need to do is we need to lock that direct sound buffer. And so basically, if you remember from the help, we basically had to use the help for Direct Sound 8 because the old Direct Sound help wasn't even there. It's probably fine to use Direct Sound 8 for any real purposes. Almost every modern machine, I think, is going to have Direct Sound 8, so I wouldn't worry about that too much. But most of this stuff works in the older API as well, so I was just calling the older version, which is Direct Sound 7 and prior. Microsoft doesn't even have the help for those posted anymore. But anyway, what we need to actually do is fill up the buffer. So we got to actually do a lock here. Where is our lock? There is our lock right there. Where don't they have? I need the actual help here, people. I want to actually see the help. There it is. This is what we're talking about. So this is the function that I actually wanted. Basically, what it does, if you remember. We are going to be doing circular buffer output, and I drew a diagram about this yesterday. I'm going to draw a diagram about it today again just to reinforce it. But basically what's happening here, right, is we have a thing that looks like this. It's a buffer, and we are going to write our sound into the buffer like this. Right, off it goes. And basically what happens here is direct sound will be playing this buffer, and when it gets to the end of the buffer, it's going to loop back to the beginning. So it's just playing it over and over. So effectively, you could think of this as a circular buffer. It's like the beginning of it was copied to the end, right? It just keeps going. It's when it plays. So as it plays, it's going to just keep going as it goes off the end. If that makes sense. So what's going to happen here is we need to basically write into this buffer. And in order to write into this buffer, direct sound actually knows that a lot of times you're using these as circular buffers. So what it allows you to do is it allows you to lock a region by giving a pointer to the beginning, basically. Not a pointer, but basically an offset, to say this is the place I want to start locking the buffer to write into. Because remember, this is a system buffer. Windows wants to know when we're writing to it. So we need to basically issue a lock call to say, we're about to write into this, so just so you know, you're going to have to update it. So we locked it to write into this, and it actually gives us back 2, potentially, regions. So for example, when we lock this, we give it a size, and maybe that size was this big, right? We say that's how many bytes we wanted to write into the buffer. So it needs to lock that big. But it can't lock that big because obviously there's nothing out here, the buffer ends. So what it does is it takes this sort of residual here, this part, and it locks the beginning of the buffer for however much the overrun was. So it basically gives us back 2 regions, right? It gives us back one region here that's at the actual offset we asked for, and that goes to the end of the buffer potentially, and one that starts at the beginning of the buffer and then goes to wherever it would have been to make the buffer the size that we wanted. Now, that doesn't have to happen. It can also be that if we gave it a pointer, or rather an offset, to somewhere in the buffer where it could lock the whole thing, just in one place, right? And this is my little lock. How's that? Oh, it's awful. Don't look at that. Okay, anyway, it'll lock it all in one chunk. So we may get back just 1, we may get back 2, and we have to handle both cases, basically, from direct sound. It's easy to do, but that's basically the idea. Hopefully that makes some sense. Okay. Let's put this up here. All right, so what we are going to try to do here, and this is where things get a little complicated, and I always mess stuff like this up. It's confusing. We need to write a little function that dumps the sawtooth into the buffer. So we're going to call this lock call here, and we are going to go ahead and call our global secondary buffer and attempt to lock it. We are going to give it the offset, and that offset is going to be something that we get from the right pointer, so that's going to be the right pointer. And we are going to try to write out, I don't know, maybe we'll basically look at the play cursor as well. We'll talk about what those two are and do it. So let's say bytes to write here. Let me see if that's actually right. It is in bytes, yes it is. Then it is going to give us back basically a series of pointer. It's going to give us a pair of pointer and size to specify those 2 regions. So this is region 0, let's say, or I guess I called it region 1 in the diagram. So we have a pointer to region 1. We have a size of region 1. So we have region 1 size. And then we're going to have this again for a second one. And that is what we're going to pass here. So we've got region 1 size, and we're going to pass the address of both of them because it's basically returning those to us. Again, it's passing the address so it can fill them out in memory. And then we're going to pass the flags, and the flags are pretty much self-explanatory here, I guess. Yeah, there's not much. Oh, okay, so you know what? We can actually lock from the right cursor directly. All right, so we can even just do that. Although we don't really want to do it that way. We want to actually specify it, I'm pretty sure. So we're gonna go ahead and say that that's the case. All right, so we don't really need any flags. As far as I can tell, there's nothing in there that's going to help us. So this is basically what we're looking at for the entirety of this call. That'll lock it for us. So now we just need, we actually need to get that right pointer, and we need to get that byte size. Right pointer, and we need the bytes to write. Let's see. Okay, so we have to actually get these from somewhere. So that's our next goal. Once we get them, we can then fill the region with a sawtooth, basically. I'm going to do that in a little bit of a sort of janky way here. Again, this is just test code. This is going to get deleted. So basically what I'm going to do is I'm just going to make this 100% explicit. I'm going to say we're going to start writing at a particular sample index, right? And that sample index is, or I should say, yeah, sample index. And that sample index is actually going to be wherever this first region actually ends up being. So yeah. Sorry, I'm not explaining this very well. This is the lack of coffee. Let me say that again. We have a sound buffer, and that sound buffer contains samples. It contains samples that look like this. It contains samples that look like this, right? They're interleaved. And basically each one of these is 16 bits, right? So it looks like this. 16-bit, it's an int16, another int16, another int16, kind of ad infinitum, right? Going on and on and on. So our buffer is 16 bits for the left channel, 16 bits for the right channel, 16 bits for the left channel, 16 bits for the right channel. So basically I want to loop over these things, and this is what we're considering a single sample, because basically they go together, right? We can't output anything less than that. We need to output one of those at a time, because that is the only thing that actually makes sense for our stereo sound. We couldn't output just 8 bits. It'd be like half of the left channel value. That doesn't make any sense. So we're going to output those at a single time. So basically, region 1 size comes back. And it had better be an even multiple of the samples. Because if it's not, something really weird has happened. Because we're only going to ask for an even multiple of the samples. The buffer is only an even multiple of sample size long. And we're not going to ever give it a right pointer that isn't an even multiple. So this would be a good place for an assert. I haven't talked to you about those yet, but we will talk about those maybe in the later of the stream to assert that that's true. Assert that region 1 size is valid. And region 2 size as well, in the case where it gets returned. So we'll talk about that a little bit later. I don't want to start throwing asserts in here until I actually have a chance to sit down and talk with you about what they are. So we'll have to schedule that at some point, because it's pretty important. Anyway, sample index is 0. It goes up to the region 1 size, and then it will be finished. Now, of course, we then have to do the same thing for the next region. So we want to go up to region 2 size, and these sample indices are relative to the region, right? So these are all the samples in region 1, these are all the samples in region 2. And what we have to basically do is we have to fill in something now. So we're going to have to fill in the pointer to something in region 2 size, and these for finished. Now, of course, we then have to do the same thing for the next region. Of course, one size as well, in the case where it gets returned. So we'll talk about that a little bit later. I don't want to start throwing asserts in here until I actually have a chance to sit down and talk with you about what they are. So we'll have to schedule that at some point, because it's pretty important. Anyway, sample index is 0. It goes up to the region 1 size, and then it will be finished. Now, of course, we then have to do the same thing for the next region. So we want to go up to region 2 size, and these sample indices are relative to the region, right? So these are all the samples in region 1, these are all the samples in region 2. And what we have to basically do is we have to fill in something now. So we're going to have to fill in the pointer to the buffer here. Basically, we're going to write 2 things, a left and a right each time. So the first thing we want to do is get an int16 pointer to the buffer. Now, it returned us the pointer, which was region 1, right? And so this is basically the sample out. This is what we're going to be writing to. So we're going to cast that to it. to an s16, which is the thing we're going to be writing. And basically, we're going to write here. We're gonna write as we increment along. We're going to write our left here and our right here, right? And then we're going to do the same exact thing down here. Does that make sense? Hopefully that's clear. All right. So basically, this will do everything that we want to. We just have to figure out what we're going to do in terms of the actual values here. So what we want to do is we want to go and every sample, depending on which sample we are at, we basically want to go ahead and make a square wave. So we want to be able to basically just do, if our sample index happens to be, you know, the first n samples, it's going to be high positive. It's the first, if it comes after that, the next n samples are going to be low and high and low and high and low. So we're going to use the mod operator for that probably. So basically what we're going to do here is we are going to actually, well, you know, we don't even really need to use the mod operator. We could be a little more janky than that. So basically what we're going to do is define a variable, and it's going to tell us where we are in our sawtooth pattern. We are basically going to call that, I'm sorry, not our sawtooth, our square wave pattern. We're going to call that our square wave counter. And basically all that's going to do is if the square wave counter happens to be 0, so we're done, you know, it's basically we've finished one part of our square wave. If the square wave counter happens to be 0, we are going to set, excuse me, man, I wish I would get healthy again. I can't tell you how frustrating it is to be trying to talk to you and have this stupid cold in my way. It is really annoying. All right. Anyway, this square wave counter is going to basically go up to the number of samples that we want our square wave to have high before it goes low and vice versa. So basically what we're going to do is we're going to say, well, if our square wave counter, I don't know, I'm going to pick a random value here and then we're going to tune it later, square wave period or something like this. We're going to reset it each time. Again, this is kind of ugly the way I'm doing this. Probably not the best way to do it, but it's the first thing I thought of. So we're going to make it do that way. And then what we're going to do is we're going to say our sample value is just going to be whether or not the square wave counter happened to be above half the square wave period. Basically, that's about it. That's all we're doing. If it happens to be above that, then it will output the highest possible value that it can. Well, maybe not the highest possible value. Let's just say 16,000. Yeah, I don't know how loud we want this thing to be. Basically, this is a 16-bit value, so 32,000 is the maximum it could be. 32, whatever it is, 65536 divided by 2. And if the square wave period, if it's not that, if it's in the other half of the square wave period, it'll output the negative. That's basically all I actually want to do here, and these are basically the exact same loop. So we'll probably compress these in a second down to one loop, but that's basically it. That is all we wanted to do. So all we really need to do now is make sure that we actually fill out all these values somewhat reasonably. I believe that's correct. Okay, someone on the stream said, let's code a mini Moog synthesizer and emulator instead of a game. You know what? That is Sean Barrett's turf, ladies and gentlemen. I am not the person to do that for you, but you know, I bet if you ask Nothings, at Nothings at Twitter, to do a stream where he codes a Moog synthesizer for you, I bet he would do that. That is exactly the kind of thing that he would do, and he is exactly the kind of person who would know how to do that a lot better than I would. I would just end up writing a lot of crappy code like this that I just wrote for you because honestly, I never synthesize sound really. I always play from some kind of sample materials that get mixed together. So this is way out of my area of expertise to say the least, but it's definitely the easiest thing for us to write to just get things going. Okay. So we need some stuff here we have not finished because we have to define some things. Obviously, we have a square wave period, and that square wave period is going to have to be something reasonable. We also have to make sure that we actually decrement our square wave counter every time we output a sample, right? Something like this, just so that it starts to count down to 0, as it should, and so it will repeat. Now, the square wave period, I don't really know what the average square wave period should be for a sound that you can hear. Let's say middle C. What is the frequency of middle C? Okay, so middle C is in hertz. Basically what hertz is, if you don't know what hertz is, it's cycles per second. Basically what that means, if I go back over here to our amazing diagram, basically what you can imagine is we had that square wave, right? It's going like this. And similarly, you might have a sound wave, that goes like this. And basically, I believe the way they typically measure it is a cycle is how long it takes to go back to where you were. So from like one peak to the next peak, right, like this, or from here to here, basically, from one complete copy of the pattern of the wave. That is basically called a cycle. That is what we're considering a cycle. And so hertz is just cycles per second. That's all. So basically, if we are going to play a sound for 1 second or fill a buffer that's 1 second long, then you can imagine it should have 261 copies of that pattern. Then you can imagine it should have 261 copies of that pattern for middle C. Basically, that is what that means. So if we try to back this out here, if we're trying to figure out what our square wave period should be, basically what the value is, maybe I'll go here and say what the hertz is. So we'll try to get a hertz, something like that. So I don't know, let's just say 256 should be close enough. I want a power of 2 just because I'm a programmer like that. That'll be somewhere close to middle C in theory, I believe. Should be fine. So if we're wanting to actually do 256 cycles per second, right? Then the question is, how many samples do we need to fill? Because again, this is going to be in samples here. How many samples do we need to fill before we actually have that many? How many samples for a full for one of our loops. So basically what we want to do is we want to say, well, hertz is samples per second, right? So all we have to really do is say that whatever our sample rate is, and we know what it is right here, we set it. So I could even say this is our samples per second, right? That we actually asked the sound buffer for. Oops. That we actually asked the sound buffer for. There it is. Samples per second. If that is our samples per second, then we basically know that if we want to have 256 of our thing, then each one of them should occupy basically the number of samples we're actually going to do in 1 second divided by the number of the things we want in 1 second, right? Because that's how many chunks there there would be. That's how many samples would be per chunk if we chunked up our full second into 256 slices. So I'm going to say that's roughly our square wave period. We're not trying to be precise here. So I'm basically going to say that that is what we will actually fill out. So now this should work, I think. We can go down. Let's see, we're writing that many samples. Yes, we are. So what we have to do here now is we have to actually turn our region sizes into counts, right? Because these are sizes, these are byte sizes that are coming back, and we actually need sample sizes. So like I said, we got to assert that they're valid, and then I jumped into an explanation and forgot to finish what I was trying to do here. We need region 1 sample count, right? Because this is how many bytes, but we know that our samples are actually 32, so that's 4 bytes per 32-bit sample, because we have two 16-bit samples, a left and a right. So basically what we have to do is we have to divide this here by our bytes per sample, right? So by our bytes per sample to actually get the region 1 sample count, which is what we want to loop over. And the same thing here, we got to do the exact same thing. What we will actually fill out. So now this should work, I think. We can go down. Let's see, we're writing that many samples. Yes, we are. So what we have to do here now is we have to actually turn our region sizes into counts, right? Because these are sizes, these are byte sizes that are coming back, and we actually need sample sizes. So like I said, we got to assert that they're valid, and then I jumped into an explanation and forgot to finish what I was trying to do here. We need region 1 sample count, right? Because this is how many bytes, but we know that our samples are actually 32, so that's 4 bytes per 32-bit sample, because we have two 16-bit samples, a left and a right. So basically what we have to do is we have to divide this here by our bytes per sample, right? So by our bytes per sample to actually get the region 1 sample count, which is what we want to loop over. And the same thing here, we got to do the exact same thing down here. And the reason I wanted to do the assertion, like I was saying, is just to guarantee that what it gave us back was evenly, excuse me, was evenly divisible here. Man, it is awful. Absolutely awful. And I don't think I've gotten much sleep the past few nights. Just don't do it. It's no good. God, all right. Well, anyway, the reason I made bytes per sample be a variable is because I knew it was used up here as well. This is it right here. So I figured we'd just clean this up, and now we'll actually have basically a complete set of definitions for our sound system that we could change if we wanted to, just to make it a little clearer what's going on. So we're going to init dsound with that exact parameter. Then we're going to go down here. We're going to do all the work with those parameters. And so pretty much the only thing we need to do now is we need to figure out where these guys are going to come from. I believe we caught everything else. I don't know, though. There's a lot of code in there, and I was talking the whole time, so there's probably some bugs, but we will debug them, and it will not be an issue. Okay. Finally, we basically need to figure out where we are going to ask direct sound to write, and we're going to have to figure out how many bytes we need to write. And we have some information we can use to do that, basically. If we go back over here to our direct sound buffer, we can see there should be a call. Let's see if I can bring up the actual definition of the buffer somewhere, people. There it is. Okay. Basically what we've got here is we've got all the calls that we can call on a buffer. And what I basically want to do is I want to get back the play cursor and the write cursor. And I'll talk about what those are. I believe it is this call right here. And this is the call that we're going to use to get that back. So right before we determine what we're going to do, I'm going to call this. We are going to assume that this succeeds, because if we can't get it, then the sound buffer died or something bad happened, and we probably shouldn't try to output sound if we can't actually get it. So I'm just going to go ahead and wrap this here right up in that so that we don't actually do anything if we can't do this. The same should be true of the lock while we're at it. The lock itself again, returns an H result. So I'm just going to say, let's not do anything if for some reason we can't lock these buffers, because that's no good. That just means direct sound has encountered some kind of really bad, sort of fatal error, bad condition. Maybe the sound card got yanked or changed out from under it or something, and we don't want to be doing anything in there. We might end up with bad writes or some bad stuff going on. All right. Now, what should happen here is basically we should be able to ask direct sound for the play cursor position and the write cursor position, and I will show you what those are. Basically, those are both going to be returned to us. If this call succeeds, we will then have that information. So there we go. And that should basically compile now, I would think. Oh, right, no, we need to call that off the secondary buffer, like that. And then we just need to do these. So there we go. Now, what are these things? Well, basically what's going to happen is, in our diagram here, I don't know if I can back up how far I can undo in this thing. Look at that. Look at that undo. Didn't quite get us far enough. All right, no big deal. We'll just go ahead and clear that out and start drawing again. Where's the pen tool in this thing? There it is. All right, so basically what happens here is in that buffer again. Oh my, why are we so tiny? Do I have to use the pen? No. How do I get a brush, people? Give me a brush. Is that a brush? There we go. All right, here is my buffer. There it is again. Basically what's going on here is you have to imagine that the hardware, the actual sound card, or the kernel mixer, or whoever is basically controlling the situation. We don't really know who that is, but whoever it is, they are actually looking at this buffer at a particular location. And that is the play cursor. That is the play cursor. Wow, that is a really bad drawing. Play cursor, right here. Now, because of the way hardware works, and because of the way the kernel mixing works, and all those sorts of things, it's all asynchronous, right? This is happening whether we're running or not. It's happening perhaps concurrently with us on a separate core of the processor. We may be interrupted at any time in our code because the operating system wants to do something, etc., etc. So these are things, the hardware, that sound is going to be playing whether we're running or not. And so it's not safe for us to start writing directly in there, because by the time we finish doing whatever the write is, the hardware may actually have beaten us, because we may get interrupted or who knows what happens. The hardware may actually have beaten us and played garbage, something that's half written or who knows what. So instead what happens is there's another cursor called the write cursor, and that basically leads the play cursor. It's a cursor that's somewhere else out here. And basically the write cursor tells us, well, we can write into a particular location, and then we can move, you know, basically from there forwards, right? And so what we're going to do is we're basically just going to see how far the write cursor moved probably, and we'll write into that. Now there's something a little bit odd here. Since the lock doesn't, as far as I know, let's take a look at this, because I'm trying to remember exactly how this system works. I don't think the lock moves the write cursor, does it? Let's take a look. Blah, blah, blah. It returns the ring buffer stuff, like we said. After writing data to the pointers returned by this method, the application must immediately call unlock. Yes, that's true. So we should actually do that. We got to do that as well. The method returns write pointers only. Yeah, so that's it. So basically, this write cursor is just going to move a little bit ahead of the play cursor. It's not going to move when we write. So one of the things we're also going to have to add here is the fact that we're going to have to track where we were in the buffer, basically. And that's really all we're going to be able to, yeah, that's what we're going to have to do. So really, the write pointer is not actually going to be something that we need to know about. Basically, it's the play cursor, really, that we're going to have to see, because we're going to have to look to see where we can fill to, basically. All right. So that's fine. It's going to be a little bit more complicated math. Like I say, this code is going to be pretty janky. Hopefully, at the end of this, we'll actually be in relatively good shape. And when we actually output sound, it'll be a lot easier than this, because we'll have abstracted this kind of weird ring buffer stuff out in a way that we don't have to deal with it. So it won't be so confusing, basically. Take an almond milk hit here. Yeah, this is probably, like I said, I told you sound was going to be rough yesterday. This is the kind of stuff I was referring to. Outputting to a ring buffer is never fun. It's always a little confusing. As we boil the code down, it'll get a little clearer. At first, it's always a little janky, especially when you don't remember how everything works, which is the case with me at this point. But anyway, point being. So, basically what we want to do is we want to actually remember where we were, how many sounds we outputted, which is sort of what we're doing here. And we want to be able to lock the buffer at wherever we left off, essentially. So since we basically have a counter, we could reuse this counter. I don't know if we really want to do that. Yeah, maybe we do. So basically what we might want to do here, for example, is we might want to just use a mod. It's inefficient, but it might be a little cleaner than what we were doing, basically, to actually get this value. So let's think about it this way. Let's say that we actually have a sample index. This is our sample index here that we're going to write to. And that's going to actually loop. We want that to be an unsigned integer because we want it to, basically, if it ever wraps over 4 billion, we want it to go back to 0, not to a negative number. So we're going to have a sample index here, basically, and that sample index is just going to go up forever for now. That's what we're going to say. And we're going to get rid of our square root counter. So we're going to have a sample index, and that's just going to go up forever. It starts at 0 and goes up forever. So the first thing that we're going to do to write into the buffer, basically, is when we lock the buffer, we're actually just going to lock the buffer at whatever our sample index is, our global sample index. So this is going to be, I don't know what we're going to call this actually. I guess let's see. Let's call this our running sample index. So it's just where it just keeps going like that. So basically what we're going to do here is we're going to say, okay, we've got this running sample index and it's going to just keep going up forever to tell us roughly where we are. We're then going to say, okay, we need to know where in the buffer that would be, because this is basically just going to go up forever and we want to map it into the circular buffer, if that makes sense. So basically we want to make a D word that is basically the sample index to lock. So this is the sample index to lock, is going to be the running sample index to lock. We're then going to say this running sample index, and it's going to just keep going up forever to tell us roughly where we are. We're then going to say, okay, we need to know where in the buffer that would be, because this is basically just going to go up forever, and we want to map it into the circular buffer, if that makes sense. So basically, we want to make a D word that is basically the sample index to lock. So this is the sample index to lock, is going to be the running sample index times the bytes per sample. So that turns it from a sample index into a byte sample, and so I should actually say, this is the bytes to lock. turns it into a where in the bytes it was. But we now have to mod by the size of the buffer, basically to say if it loops, when it gets to the end, it's got to go back to the beginning because it's in this circular buffer, right? Right? Now the mod is basically just says remainder. It basically says divide this number by this other number and give me the remainder, which is exactly what we want, right? We basically want it to give us something back that's going to be, excuse me, that's going to be whatever fractional portion we would have of the total buffer size, because that's where in the buffer we will actually be. So that's what we actually want here. We want that byte to lock. So that is what we'll be asking, byte to lock, right there, right? And then the number of bytes to write is basically going to be however far we would go to get to the play cursor, because we don't want to write past the play cursor. So we're just going to write from wherever we are to the play cursor. So basically, here we go. We have got our bytes to write. And basically what we need to know is we need to know whether the play cursor is in front of or behind the byte to lock. So basically, if the byte to lock is actually in front of, right, the play cursor, if it's higher than where the play cursor is, because this play cursor, again, is also going to be in bytes, I believe. Let's verify that. I don't actually know. We didn't look. Let's take a look. Address of the variable that returns the offset in bytes. That's what we want to know. So basically, if the byte to lock is above the play cursor, that means we have to write all the way to the end of the buffer and then from the beginning to the play cursor. So basically, that means that our bytes to write, which is what we're trying to compute here, our bytes to write is basically going to be the buffer size, right? So this is the, I should say secondary buffer size, just so we're clear about this. The secondary buffer size minus wherever the byte to lock is. That's how far we had to go. Again, to go back to the diagram, basically, I know this sounds complicated and there's tons of finicky math in here, but not really, it's arithmetic, really. Basically, what I'm saying is we've got two cases. In fact, let me go ahead and clear that out so I can show the two cases. So basically, we have case 1 and case 2, and we got to handle both of them. So in one case, this is our byte to write here, right? And here was the play cursor. This is byte to write, not the right cursor. The right cursor is somewhere in here, but we're ignoring the right cursor. We don't even care where it is. So what I'm saying is, if this is our byte to write, and we see that the play cursor is here, then we know that it's safe to fill this part of the buffer and this part of the buffer. And this is the region we don't want to touch, because basically anywhere in here we don't want to touch, because we already wrote it and the play cursor is still playing, still hasn't played that part yet, if that makes sense. So basically what we're going to do is we're going to look at this and we're going to say, okay, if the byte to write basically is greater than the play cursor, right? If it's greater than it, then we need to do two chunks, that chunk and this chunk. On the other hand, if the opposite was true, if here's the byte to write, this is our byte to write, and this is our play cursor, then we only have one chunk. We only have this chunk here, right? This is case 2. So if case 1, case 2. Hopefully that makes some sense. That is what I'm trying to write here. So basically this is the case, this is that case 1 at the top, when byte to lock is above the play cursor. Basically what we need to do is we need to take the secondary buffer size, so the total buffer size, which is, you know, this whole thing here, we're taking that total buffer size, and we're subtracting this value from it, so that we're just producing that number right there, right? And then we also need to add the part at the beginning of the buffer. So we're basically going to add wherever that play cursor was, because we got to play from 0 to that, right? Makes some sense. On the other hand, if they're the other way around, then we just have a very simple thing to do, which is say however far is between those two cursors is how much we're going to write. that is how much we're going to write. So then we go in here and we do the lock. We do the lock with that bytes to write. And then what we do is we basically say, okay, our square wave counter is still in effect, but actually, I guess, like I said, we could get rid of that with a mod. I'll show you how to do that in 1 second. Basically, this is all about modding. Maybe we should have a little discussion about modding in the Q&A. Since we never really covered modding, we'll talk about it in a little more detail. It's kind of something that's interesting to know. So basically, we are going to go in here, and we are going to do the to-region thing, like that, like we wanted to. There we go. And we will be writing our stuff as we wanted to. And then so the only thing we have to do is change our sample value to basically be this if statement. Instead is just going to be on our square wave period, our running sample count, our sample index rather, mod the square wave period should basically be what we want to do. Is that correct? No, sorry, divided by the square wave period. Divided by 2. Yeah. Oh man, this is a little nuts, but I think that's it. If the running sample index divided by half the period, that's either going to be 0 or 1. So we got to mod that. Yeah, that's a little annoying. So I'm going to make a secondary variable for that, and then I'll explain it, assuming that I did it right. Half. We want the half square wave period. Half square wave period equals square wave period divided by 2. There we go. And so all I'm trying to do here is basically just say, so if we have we divide this out by half the square wave period, then basically what we're going to get is which half period we're on, right? Basically, if I have a sample index and it's going up and I divide it by half the period, we're going to say it's going to be 0 in the first half period, 1 in the next one, then 2 in the next one, then 3 in the next one. So basically, if you imagine what I'm doing with that divide, if this is our square wave, right? Basically, you can imagine what I'm doing is dividing by half the period. This is half the period, right? This is half period here. I'm dividing by that. So that basically what that'll give me back is just an integer that counts up for which half period I'm in. It'll go 0, 1, 2, 3, 4, 5, 6, and so on, right? So all I have to then do is look if the number is even, right? If the number is even, we should be high. If it's negative, we should be low, or vice versa. We don't care which phase our thing is. So basically what I got to do there is I got to mod it by 2. I got to take the mod 2, which says basically 0 or 1, whatever the remainder is when you divide by 2, that is the thing that's going to be it. Oops, this is actually, just goes back in there. So that's what I'm trying to do here. There you go. And that should be just about it. The buffer size, again, we got to actually put in here because that's used now, secondary buffer size, and we already, again, compute that right there, secondary buffer size. And you'll notice that a lot of these things kind of work themselves out. Again, this is why I always say compression-oriented programming is the best way to do things. You'll note that basically all I do when I'm trying to write code that's somewhat complicated like this, and that's sort of finicky, is I just keep writing whatever the most obvious thing is to write at the time. I don't try to overthink it, and then the patterns just kind of emerge. You can see everything here. In fact, you can even see where we're going to go with this eventually. You can see how these two loops are the same. So we'll probably boil that down and so on. And basically you just keep pulling stuff out that's common. That is the best way to end up with nice working code that does exactly what you wanted to do instead of trying to front load it. Okay, I gotta blow my nose here, people. There's really not much I can do about it. It is awful. All right, let's see here. I think we We've basically done everything, but let's just do a quick spot check because there are probably some bugs in this given how many things happened here. Let's just do a quick once over just so we understand everything that we're trying to do, and then we'll go debug it. So basically, we basically made our hertz here. I'm going to call this our tone hertz because it's basically saying our tone samples per second. However, in the screen that says gross, it is totally true. It's awfully gross. I have to live with it. I have to live with it, man. That is the thing. I've been living with this for like a week. It's awful. The cautionary tale, do not get sick, people. That is what I'm telling you. Do not get sick. I'm hoping maybe I'll start feeling better later today or tomorrow. It's been a long time. All right, anyway, this is our sound stuff here. This was for our graphics test, and this is for our sound test. They are not similar at all. Okay, sound test. So we have our samples per second. That's 48 kilohertz. That's how many we're playing. We have our tone hertz, and that's tones per. This is per second as well. We might want to call this sample hertz, but I don't know. It's 6 and 1/2 dozen the other. Our tone hertz is basically 256. So we are taking our samples per second and dividing that by the tone hertz. That's how many we want. We have a half square wave period, which is going to be whatever that period is divided by 2, and that's because we want to know ups and downs. So we want to be able to divide by that. We have our bytes per sample, which basically tells us how ups and downs. We have a half square wave period, which is going to be whatever that period is divided by 2, and that's because we want to know ups and downs. So we want to be able to divide by that. We have our bytes, which is going to be whatever that period is. Dividing that by the tone hertz, that's how many we want. We have a half square wave period, which is going to be whatever that period is divided by 2, and that's because we want to know ups and downs, so we want to be able to divide by that. We have our bytes per sample, which basically tells us how many bytes we take to write one left-right pair, each at 16 bits. So that's times 2, 16 bits. We have our secondary buffer size, which is however many samples per second times the bytes per sample, because we know we have a 1-second buffer. That's basically what we define it to be. So we init direct sound with that, and that should be basically everything that we needed there. I'm going to double check the Win32 inits dsound function to make sure that that is what that takes, samples per second and buffer size. That's good. That all works. All right, so we then come in here, and now we actually do all the craziness. We ask where the play cursor and the right cursor is, even though we don't actually care where the right cursor is. So we ask where the play cursor is, essentially. And let's make sure we have those in the right order. Yep, play cursor first. So that's good. We then get the byte to lock by taking however many samples we are in. Ah, there's the thing we forgot. I knew we forgot something. Plus running sample index. We got to add that every time through. So we take our running sample index, we multiply that by the bytes per sample to basically get where we are in the running bytes. So basically an infinitely increasing, until we wrap the actual value, the actual variable, an infinitely increasing value of bytes. So then we use the mod to map that into the secondary buffer where we are in the actual buffer, because remember it's kind of this circular buffer thing. So we need to take this long linear thing and wrap it into an actual buffer. We then say if the byte to lock was after the play cursor, then we take two pieces. We're basically going to do two locks. We're basically going to have to fill two regions. We're going to fill the secondary buffer size minus the bytes to lock, and then we're going to fill the play cursor's worth from the beginning of the play cursor's worth. Otherwise, we just fill the distance in between them. That seems totally reasonable. We then go through here and we ask to lock exactly that. So we should get back, in case one, we'll get, 5-minute warning, almost there. We should get back either the 2 chunks in this case or the 1 chunk in this other case. Assuming that we do get them back, we then go ahead and we figure out what the region sample counts are. We point to the first region here. Let's do it this way, just to make that a little clearer. we point to the first region. We find out how many bytes, how many samples we got to fill for that one. We go ahead here and we actually loop through all of those samples. We add to the running sample index each time. In fact, we could even stick that right in there. Make that a little clearer that that's only getting used just in that one place. There we go. We write out both a left and right value. They are exactly the same, so that's good. We go